Hello, my name is Abhidhar Joshi and I'm going to give a presentation on hidden Markov models. So let's get started. First of all, we'll talk about the contents of the presentation. We'll start off the presentation with the introduction about the hidden Markov models. Then we'll talk about the Markov chain property and model. Then we'll talk about the types of Markov models. We'll move ahead and we'll discuss further about hidden Markov model versus the simpler Markov models. Then we'll explain the whether hidden Markov model with an example. After that, we'll talk about the learning and mathematical description, and we'll wrap the presentation with 3 basic problems and applications of the HMM. So the introduction. So what is the hidden Markov models all about? So the hidden Markov model is a relatively simple way to model sequential data. A hidden Markov model implies that a Markov model underlying the data is hidden or unknown to you. More specifically, you know only observational data and not the information about the states. In other words, there is a specific type of model that produces a data called a Markov model, which we'll discuss in the next slide, but you don't know what processes are producing it. You basically used your knowledge of Markov model to make an educated guess about the model structure. So let's talk about the Markov chain, Markov property, and Markov model. So what is a Markov chain? A Markov chain is a stochastic model describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. So that is Markov chain in simple words. Now let's go ahead and talk about Markov property. So Markov property is a stochastic model which is used to model randomly changing systems. These are all called Markov models, Markov chain, and Markov property because they're basically named after a Russian mathematician called Andrei Markov. That's why we have used Markov everywhere. So it is basically assumed that the future states depend only on the current state and not on the events that occurred before it. In the field of predictive modeling and probabilistic forecasting, it is desirable for a given model to exhibit a Markov property. Now we've coined the word Markov property. So let's talk about what is Markov property. So Markov property basically refers to the memoryless property of a stochastic process. So now, since we have the terms clear, let's go ahead and talk about different types of Markov models. So there are 4 common Markov models which are used in different situations, and it depends on whether every sequential state is observable or not and whether the system is to be adjusted on the basis of observations made. So these are the 4 types of observations. The first one is called the Markov chain. It is the simplest Markov model in the Markov chain. It models the state of a system with a random variable that changes through time. In this context, the Markov property suggests that the distribution for this variable depends only on the distribution of previous state. An example use of Markov chain is Markov chain Monte Carlo, which uses the Markov property to prove that a particular method for performing a random walk will sample from the joint distribution. The second one is called the hidden Markov model, which is the topic of today's presentation. So hidden Markov model is a Markov chain basically which the state is only partially observable. In other words, the observations are related to the state of the system, but they are typically insufficient to precisely determine the state. Several well-known algorithms for hidden Markov models exist, like the Viterbi algorithm, the forward algorithm, and the Baum-Welch algorithm. Now what are the use of the HMM or the hidden Markov model? So one common use is for the speech recognition, where the observed data is the speech audio waveform and the hidden state is the spoken text. In this example, the Viterbi algorithm finds the most likely sequence of the spoken words given the speech audio. Now that was the second one, which was the hidden Markov model. Let's go ahead and talk about the third type of Markov model called the Markov decision process. So a Markov decision process is a Markov chain in which the state transitions depend on the current state and an action vector that is applied to them. Typically, A Markov decision process is used to compute a policy of actions that will maximize some utility with respect to expected rewards. It is closely related to reinforcement learning and can be solved with value iteration and related methods. And the fourth type of Markov model is called the partially observable Markov decision process, or POMDP. A partially observable Markov decision process is a Markov decision process in which the state of the system is only partially observed. They are known to be NP-complete, but recent approximation techniques have made them useful for a variety of applications such as controlling simple agents or robots. So these are the four types of Markov models. Now let's talk more about the hidden Markov model and how it is different from the simpler Markov models. So hidden Markov model is a statistical Markov model in which the system being modeled is assumed to be Markov process with unobserved, or you can say hidden, states. The hidden Markov model can be represented as the simplest dynamic Bayesian network. In the simpler Markov models, like the Markov chain, the state is directly visible to the observer and therefore the state transition probabilities are only parameters. While in the Markov model, the state is not directly visible, but the output, which is in the form of data or token, which is dependent on that state, is visible. Each state has a probability distribution over the possible output tokens. Therefore, the sequence of tokens generated by an HMM gives some information about the sequence of states. This is also known as pattern theory. Now let's talk about what is hidden in the hidden Markov models. So the adjective hidden refers to the state sequence through which the model passes, not to the parameters of the model. So the model is just still referred to as hidden Markov model even if these parameters are known exactly. And let's just take it to the example for further understanding. So one classic example which is used around the globe for the HMM is the weather HMM. So consider two friends, Alice and Bob, who live far apart from each other and who talk together regularly over the telephone about what they did the specific day. So the Bob is only interested in doing three activities. The first one is walking in the park, the second one is shopping, and the third one is cleaning. So these are the three activities in which Bob is interested. The choice of what to do, to be specific, which activity to do, is determined exclusively by the weather on that specific day. Now Alice has no definite information about the weather, but she knows some general trends. Based on what Bob tells her he did, Alice tries to guess what was the weather must have been like. So Alice believes that the weather operates as a discrete Markov chain. There are two states, the runny and sunny, but she cannot observe them directly. That is, the states are hidden from her. On each day, there is a certain chance that Bob will perform one of the following activities: walk, shop, or clean. And obviously, it will depend on the weather, whether it's rainy or sunny. Since Bob tells Alice about his activities, those are the observations. The entire system is that of a hidden Markov model. Alice knows the general weather trends in the area and what Bob likes to do on average. In other words, the parameters of HMM are known. Let's move on to the next slide and discuss this problem further. So Alice believes that the weather operates as a discrete Markov chain, and there are two states, the sunny and the rainy state. So the states, as you can see, is the rainy and the sunny, and the observations made by Alice is walk, shop, or clean. In this piece of code, as you can see, the start underscore probability, it basically represents Alice's belief about what state the HMM is in when Bob first calls her. All she knows is that it tends to be rainy on average. The particular probability distribution used here is not the equilibrium one, which is given the transition probabilities approximately rainy equals 0.7 and sunny equals 0.43. The sum has to be 1, obviously. The transition underscore probability represents the change of weather in the underlying Markov chain. In this example, there is only a 30% chance that tomorrow will be sunny if today is rainy. And last one, the emission underscore probability represent how likely Bob is to perform a certain activity on each day. If it is raining, there is a 50% chance that he is cleaning his apartment. If it's sunny, there is a 60% chance that he is outside for a walk. So this is basically a typical example of a weather HMM. Now let's talk about the learning and the mathematical description. The parameter learning task in HMM is to find, basically, given output sequence or a set of such sequences, the best set of state transition and emission probabilities. The task is usually to derive the maximum likelihood estimate of the parameters of the HMM given the set of output sequences. Now the mathematical description. A basic hidden Markov model can be described as follows. So these are the terms which are typically used in the hidden Markov model. N is the number of states, T is the number of observations, theta I minus 1 to N, that is the emissions parameter for an observation associated with the state I, phi I equal to 1 to N, and J1 to N, that's the probability of transition from the state I to J. Phi I from 1 to N is the n-dimensional vector composed of phi I J1 to N, which is the ith row of the matrix. Xt, which is 1 to T, that's the hidden state n in time, and yt is basically the observation. So x is the state and y is the observation. X is hidden from us and y is basically what we see. The function f of y given theta is the probability distribution of an observation, which is basically parameterized on theta. Xt from 2 to t is categorical, phi xt minus 1, and yt minus 1 to t is almost equal to function f of theta given xt. Note that the model, the prior distribution of initial state x1 is not specified. So the typical learning models correspond to assuming a discrete uniform distribution over the possible states. That is, no particular prior distribution is taken under any assumption. Now the three basic problems and applications. So the three basic problems which can be solved with HMM or the hidden Markov models are as follows. Given the hidden Markov model lambda, which is the a, b and pi, and a sequence of observations O, find the probability of observation PO given lambda. This type of problems is called the evaluation problem. The second one is, given the hidden Markov model lambda, function of a, b, pi, and an observation sequence O, find the most likely state sequence, which is like the S1, S2, S3 and so on. This is sometimes called the decoding problem. And the third one is called the learning problem or the optimization problem. The goal of this problem is to find an observation sequence O1 to 3 to On and hidden Markov model lambda in function of a, b and pi that maximizes the probability of O. So these are the three basic problems which can be solved with the help of HMM or the hidden Markov models. Now let's have a look at what are the applications of the HMMs. So the hidden Markov models are especially known for their application in reinforcement learning and temporal pattern recognition. They're also applied in computational finance, extensively used in speech recognition and gene prediction. They are also used in handwriting recognition and time series analysis. So that was the presentation about the hidden Markov models. Thank you and have a great day.